Okay, so where we left off, we had just talked about chemistry being the study of matter, which is stuff all around us, and this is where we left off. And let's talk about atomic structure. Okay, you know that they consist of three subatomic particles: the proton, the electron, and the neutron. And the proton and the neutron, those two are in the nucleus of the atom, and the electron is going around, and my dog's barking. This is in the outer shell of the atom, okay? In chemistry, for the most part, we're not going to be involved with the nucleus. Those particles are held together so tightly that anything we do isn't going to affect the nucleus, okay? And it's just great dog. So we will talk a little bit about nuclear chemistry and radioactive decay and so forth, but for the most part, we are going to be concerned with the electrons, okay? One picture of the atom is that the nucleus has these different particles in the center, protons and neutrons. They're bonded together, and then around them in shells are the electrons. And these are this model, see 1, 2, 3, 4, 5, 6, 7, 8. This is called the Bohr atom. Niels Bohr was a Danish physicist who proposed this. And I'll be right back. And these energy levels were determined by looking at the light that is absorbed or given off by different elements. And that has to do with the electrons moving from one energy level or one shell to another shell. So if this electron could jump up, and it can't jump into this shell because it's full, but if it could, it would absorb some energy of a specific amount. And when the electron falls back down, it would give off an energy of that same specific amount. So one is absorption, the other is emission of electromagnetic radiation or light. And you might remember learning about the electromagnetic spectrum, different energies of light and different wavelengths. And the energy involved with moving an electron from one shell to another is generally in the ultraviolet. There's some in the visible, and that those electron transitions are what gives things their color, and some in the infrared too. Okay, so there is another more detailed model or picture of the atom, and we call that the quantum mechanical model, where these shells of the Bohr atom are divided into subshells. And you might remember we use the letters S, P, D, and F to describe those subshells. And each subshell is divided into a number of identical orbitals. The S has 1 orbital, the P has 3, D has 5, F has 7. Okay, for our purposes, we're mostly going to focus on elements with S, P, D, and F subshells. We're not going to worry about elements where electrons are populating the F subshell. They're important, they're very important in technology, but there's not a lot to be gained from getting into that, and we can avoid some complication. So when you go on in chemistry, you'll learn more about the F elements. So the S subshell is spherical. Remember, there's one of those. The nucleus is at the center. The P subshell is this hourglass, and the nucleus is right at the center here. And this is three-dimensional, so it's a two-lobed structure, not a figure 8, but more like an hourglass, or we said peanut in class. And there are 3 of these: one this direction, one would be oriented this way, and one would be that way. So we have along the 3 X, Y, and Z axes. I'm not going to draw all 3 of them. The D has 4 lobes, and there are 5 of these in various orientations, and you can look in your book or look online to see those. And the F is a more complicated shape. Let's see if we can predict how many lobes. 1, 2, 4. Oh, we're doubling each time. There are 8 lobes in an F orbital. Okay, just like there's a pattern here, 1, 3, 5, 7 for the number of orbitals. We're going up by 2 each time. Okay, so the electrons go into these subshells in order, beginning with the first shell, which has only an S subshell. So we call that 1s. The second shell has an S, and it also has a P. The third shell has an S, a P, and a D. The fourth has an S, a P, a D, and an F. The fifth has an S, P, D, and F, and there's a G, but there aren't enough electrons in those atoms or on the periodic table to populate G subshells. And the sixth shell goes past G to H. Okay, but we don't have to worry about anything past F. In a hydrogen atom, an atom with one electron, if I put energy increasing this way, in a given shell, all the subshells have the same energy. And I'm using a horizontal line to represent the energy of an orbital in a particular subshell in a particular shell. So there's one line for the 1s because S has one orbital, as I said down here. There are 3 lines for the P because a P subshell has 3 orbitals. And the for the third shell, we have 5 for the D. And for the fourth shell, 4s, 4p, 4d, and 4f. All the same energy, 3, 4, 5, 6, 7. You get the idea. This is for hydrogen only. As soon as we add a second electron to an atom, these energies shift. And I'm going to see if I can select, can I do this? And move this up, say, not with my arrows. Ooh, didn't mean to do that. Okay, so they shift up, and now let's see if I can shift these guys up. Okay, good. And here we run into an interesting thing because we're going to put electrons starting at the very lowest energy, and I'm going to represent the electrons as arrows, and the arrows point opposite ways because the electrons have different spin. Remember, this is just a review, so you might have to review that. So 1 arrow up, 1 arrow down. 2 electrons, they must have opposite spin. And then when we fill these, we put them all in with the same spin. That's called Hund's rule.